Good evening. Welcome back, Mustangs, for another edition of No Hair, No Problem. Today, we're going to be jumping into a subject that relates to binomial theorems. And this is not so much, I would say, like mathematical as it is just simply applying a formula to something and learning how to expand a binomial. Let's get started. It's pretty easy. It's just following a pattern. So let's talk about those patterns as they kind of come up, okay? So with binomial theorems in 8.4 here, there's a process that you can multiply all these out and kind of see a pattern start to form with all these, okay? So for example, if I said we had x plus y, and again, we're talking about binomial expansion here. So we're talking about taking some binomial and expanding it out to a longer form. So if we were to look at, say, something to the 0 power, anything to the 0 power, we all know it's 1, right? So there's nothing really special about that one. If we go ahead and say x plus y to the first power, anything in the first power just stays exactly as it is. So we're going to end up with just an x plus y. Now, when we start doing bigger ones, like when we do x plus y to the second, remember what we're saying is that x plus y squared is the same as saying x plus y times x plus y. And there's a little pattern that starts to develop as we work through this. That when I take the x and I distribute it to both parts here, we have x squared and then we have an xy. And then we have an xy when we multiply the middle, and then another y squared at the end here. And when we add these up, we have x squared, we have two xy's, and then we have a y squared. Okay. Now you don't see this pattern yet, but it's going to start to unveil itself here as we get to higher degrees. So we're going to go to the third power, which this is the same as if I just go ahead and multiply out by another x plus y in here. And then to the fourth power would be like if I multiplied by another xy. And here's what happens when we look at this. Now, you may not see the pattern right away, but there is actually a pattern here. And I'll mention it again in like written form here, but I want you guys to actually see the pattern. Take a look at the numbers that we see here. We see a 1, there's a 2, and then there's another 1. You should sense there's some symmetry right there, okay? When I look here, you see 1, 3, 3, 1. There's symmetry there. When we see 1, 4, 6, 4, and then there's a 1, there is symmetry there, okay? When we look at the variables, we see an x to the second, x to the first, and then we see no x. So 2, 1, none. We see in the next one, 3, 2, 1, and then none. We see in the fourth one, 4, 3, 2, 1, and then none. Now that's just for the x, but what about when we're looking at the y? Well, for the y, it actually goes the other direction. Watch. 2, 1, none. 3, 2, 1, none. 4, 3, 2, 1, none. And so because of this pattern, we can quickly then write larger ones in an expanded form. So for example, before I actually show the answer for this one in a nice clean format, let's go through and do it really quickly. And let's look at the values that we have here. And the other thing was, sorry, if you look at the values from up above, I'll show this in a better form here, but 1, 2 adds up to 3. 2, 1 adds up to 3, okay? You'll notice here that 1, 3 adds up to 4. 3, 3 adds up to 6. 3, 1 adds up to 4. And what's happening is we have a pattern that's going to form, which we're going to actually call, you've all seen this before actually. It actually relates to Pascal's triangle. So let's actually jump down there really quickly before I get back up here to the fifth, x plus y to the fifth power, okay? So when we look at Pascal's triangle here, these are numbers that we see a pattern forming here. We have ones going all the way down diagonally here, and then we have ones going all the way diagonally down here. But more importantly, look at what happens when we look at the sums, okay? Sorry, right here. We get that 1 plus 1 adds up to 2. And we can see this pattern go through the entire shape, that 2 plus 1 adds up to 3. 2 plus 1 adds up to 3. 3 plus 1 adds up to 4. 4 plus 6 adds up to 10. The two values up above will always add up to the value that's down below it. So when we look at this, the formula that's taking place is x to the 0 power, x to the first power, x to the second power, x to the third power, x to the fourth power, and x to the fifth power. And here we are now where we said, going back, sorry, we're jumping back here. We said we're doing x plus y to the fifth power. Now the numbers that we're going to use are going to come actually from Pascal's triangle, but we'll get to how that gets used later. But it's 1, 5, 10, 10, 5, 1. So I'm going to use those values up here and watch. 1, 5, 10, 10, 5, 1. Okay. Now let's take those x values that we were just talking about. This x right here is x to the fifth, x to the fourth, x to the third, x to the second, x to the first, and then x to the 0, or just no x. Okay. And that x to the first, we don't generally write the 1, it's just an x. Okay. For the y that's right there, we're going to go the other direction. We're going to have y to the fifth, y to the fourth, y to the third, y to the second, y to the first, and then just y to the 0. But again, 0 becomes nothing. What does that look like in the cleaned up form? Boom. That is the expansion for x plus y to the fifth power. You could see it's actually the exact same thing. So if we were to do it with the sixth power, we go ahead and use Pascal's triangle right there, and we can go ahead and get that this is the expanded form that takes place for this. So as I said, there's several observations that you should make when you're looking at these, okay? The first is in each expansion, there are n plus 1 terms. Now, what does that mean? When we look at this, I said we're going to do 6, right? So 6 is my n in this. Well, you'll notice there's 1, 2, 3, 4, 5, 6, 7. So there are 7 terms in this expansion. It's always one more than the actual power that's taking place. So that's the first thing you should recognize in this pattern, okay? The next thing we should see in this pattern is that in every expansion, x and y have symmetric roles. The power of x decreases by 1, and then the power of y increases by 1. So as I said, you can see a pattern go on here. We go 6, 5, 4, 3, 2, 1, and then none. However, going in the other direction, we go from 0, 1, 2, 3, 4, 5, 6. Okay? So that's that pattern that happens with the degrees. Okay? There's another pattern that actually forms with the degrees. The sum of the powers in each term is n. What does that mean? Well, if my power in this, we said, was equal to 5, look at what happens when I look at the expansion of this. Your powers are always going to add up to 5, so there's just a 5 right there. 4 plus 1 adds up to 5. 3 plus 2 adds up to 5. 2 plus 3 adds up to 5. 1 plus 4 adds up to 5, and then 5 is just 5. Okay? And then there's one more thing that happens in the pattern is that the coefficients increase and then decrease, and those are symmetrical. And I said this before, that we have, when we look at the pattern for this, we have a 1, 5, 10. It's increasing. And then it decreases in that symmetric pattern of 10, 5, 1. Okay? So that's the pattern. And again, this is actually derived from Pascal's triangle. And so what we can see is when we look at larger expansions, you can see the expansion of Pascal's triangle take place here. I'll actually show you where the numbers coincide. When we look at a 1, we just have a 1, obviously. 1, 1 and 1. 1, oh, my hand, look at that. 1, 2, 1, 1, 2, 1. Okay. 1, 3, 3, 1, 1, 3, 3, 1, and so on and so forth. You could see this expansion taking place here. So that's Pascal's triangle. But what about if I wanted to use some basic formulas? Well, this is where we can do a binomial coefficient. And in order to do this, we can actually derive this from the letter C, which has to do with combinations, which we'll talk about more in the next section. But that talks about combinations, and what we're saying is we have 3 and then 0. So where we have 3 for the n, and then 0 for the r, this is my n, this is my r, there's a little formula that actually creates these values of 1, 3, 3, and 1. Now, what is that formula? Okay, I'm sorry, I wanted to show you it in Pascal's triangle there. I'm sorry, in the expansion, that one we get 1, 3, 3, 1 using that little formula. Now, what is that formula? Well, those binomial coefficients actually come from this right here. Okay, and we'll talk more about some of the other formulas that are in here in a second. But the one that's really important is this one right here. This is a formula that tells us if I'm trying to find a specific term within our entire expansion, in our entire sequence that's taking place. And that's a formula that it looks a little bit crazy, but you find it's actually really not too challenging once we get the hang of it, okay? And this formula you really don't have to memorize. It's actually built directly into our calculators. And there's a shorthand way of even writing that, which is this right here. These two are exactly the same. So there's like a little symbol we use for that. But this is the one that's actually in our calculators that we're going to use. Okay, and I'll show you guys where to find that here in a moment. Okay, and we'll get to this expansion formula right here in a moment as well. So let's start with first, let's practice that NCR formula there. And so when we look at, we're finding the binomial coefficients of 8C2 and 10.3 and 7.0 and 8.8. Let's take a look at what these actually look like, okay? So that 8C2 stands for, when we do this is my N, this is my R. The formula again is 8 factorial divided by, I didn't want to write 8, sorry. It is N factorial divided by N minus R factorial and then R factorial. And so literally you're just plugging those values in there. Now what ends up happening is when we write these out, that remember that factorial means we go 8 times 7 times 6 times 5, and then that 6 on the bottom is 6 times 5 times 4, and so on and so forth, right? So if we look at the expansion of this, we're trying to get the factorials to converge on each other. So 8 times 7, and then we get to that 6 factorial, and we notice that these 6's right here can go ahead and just cancel each other out, leaving me with 8 times 7 on the top, and then 2 on the bottom. And that means we end up with a 28 for the actual value here. That would be the coefficient if I was looking at Pascal's triangle there, okay? If I was to do 10 and 3, same exact 3, I would go, same exact thing. I would go 10 factorial, 10 minus 10 minus 3, which is 7, and then 3 factorial. That 10 is going to get dropped down until it meets up with the 7, so we get that 7 factorial there. We're left with 10 times 9 times 8, which is 720, divided by 6, which is going to give us 120. That would be my coefficient there. If we look at 7C0, it means we're going to go 7 factorial divided by 7 minus 0 factorial times 0 factorial. Now, if these disappear, it would be like, what am I going to do? I'm going to divide by 0. Well, if you remember one of our rules, we said that 0 factorial is the same as equal to 1. We did that in our last section. And so we end up with 1 divided by 1, which is just 1. So anytime you have a 0 here for the 7C0, 9C0, 4C0, it always ends up equaling 1. That's a rule. And then when I have 8 over 8, 8n and r, 8 for n, 8 for r, we're going to have 8 factorial divided by 8 minus 8 factorial. Remember, this is an 8 minus 8 factorial because n minus r. That gives us that 0 factorial. And then we're going to have a 1 again. So these two are going to end up being exactly the same always. If we share the same value for n as we do r, it's a 1. And if we have a 0 embedded in there, it's a 1. Okay. Now, how do we do this on the calculator? Let me show you where they are on both calculators. So on our graphing calculators, you're going to go to this math button right here. Okay. And inside your math button right here, you're going to hit... you're going to go to the top right here, which says probability. PRB stands for probability. And in there, you're going to see the button right here under number 3 that says NCR. Now, you don't have to scroll down. You can just actually hit 3, and it pulls it up. So let's say I put in an 8, and then I put in an 8 for that little square. We will get a 1. Okay. So that's where it's located on our graphing calculator under math and then probability again. So you go math, and then you go probability. PRB, okay? And then on the Desmos here, you can actually find this in your calculator under functions. So let me get myself out of the way here because I'm always in the way. But under functions here, if you go all the way down to the bottom, it's actually right at the very, very bottom there. You'll see it says NCR. Now this one's a little different when you put it in. This one, you have to define the two values n and r separated by a comma. So we would say 8, comma 8, 8, and then parenthesis, and you'll see it ends up equaling a 1. Okay, and if it was like a 7, let's go with it again, go function, and let's go down to NCR, and let's put in like 7, comma 0, we know it should equal 1, and sure enough it does. Okay. All right, so let's get back to our notes here and let's actually practice doing some expansions. Sometimes when we're doing these, we're asked to actually find a very specific value. So it might say find the third terms, find the 15th term, find the ninth term, whatever it might be. And there's a little like process that happens to these, okay? What we should recognize in the binomial theorem is that when we're saying you can use the fact that from the binomial theorem, the r plus 1th term is. So when we're saying r plus 1th term, what in God's name are we talking about? Well, this is that formula that was just up above in the yellow there, that NCR, x n minus r, and y r. So if I was to say find the 6th term in the series, we're saying find the 6th term in the series, what are we going to be finding here? Well, here's our formula. It says because the formula is for the r plus 1th term, so it says the 6th term, that means that if r plus 1 is equal to 6th term, my r value is going to simply equal 5. Okay, now bear with me. It says 6th term, my r value is going to be 5. It's always going to be one less. So to find the 6th term in the binomial expansion, we're going to use that formula. It's going to be that there's, when you look at this, there are 8 for the n. So it's going to be 8, c, and then 5. The a term right here is going to be a, okay? And when we look at the formula here, going back, it says we're going to have n minus r for this portion right here, and then r for this portion right here. So what we're going to have is 8 minus 5, and then we're going to have 2b to the 5. Okay? That's it. That's literally all you have to do to set this up. Okay? So again, this number 8 is the n. That's the power of this. This value right here is always 1 less than the term they're asking us to find. So if they say find 6, we're going to find the 5th. This portion right here is always going to be subtracting these two. And this portion right here is going to be the r value, which is this second part that's right there. That's it. So that's the formula, okay? So you set this up, and this is what it looks like. So we have 8c5, a to the 8 minus 5, and then 2b to the 5th power. So let's clean all this up and see what we actually get here, okay? This value, when we put it into our calculator, we have 8c5 is going to give us a 56. That 8 minus 5 will give us a 3, and then we have a 5 right here. Now again, one of our patterns we should recognize is that this will always add up to the power of our binomial, which is 8, so 3 plus 5 is 8. We have to take this 2 and expand it. Now 2 to the 5th power, hopefully you know, is 32. So what's going to happen is we're going to have 56 times 32, which will give us 1,792, a third, b fifth. That's it. That's the 6th term in our series, okay? For the, what is it? For letter B, it says find the coefficient of the term 6, 5. Okay, now they're saying 6 and 5. Those are the two values of the, that's the expansion right there of the 6 and 5. So which term are we actually finding here? Well, when we look at this, we know that 2a minus 5b to the 11th power. Why do we know it's the 11th power? Well, that's because, first of all, they give us it's the 11th power, but we also know that the 6 and the 5 adds up to 11. Okay? So when we go to expand this out, what we have to say is, again, the formula actually is very specific. It says that we have to have this whole value is being raised to this power, right? So we have to make sure that when we set this up, that negative 5b is being taken, not a positive 5b, okay? So what is it that we're looking at here? Well, if we look at the total power, which is 11, okay, when we look at the, what are we asked to find? The coefficient of a6, b5. So if we say a6, b5, remember the formula here says that this is really 11 minus 5, b5. This is really a to the n minus r, b to the r. That's our formula, right? Remember this, okay? So if we work backwards here, continue working backwards here, we know that if we set this up, we have 11C5, okay? We have 2a being raised to the 6th power. We have negative 5 being raised to the 5th power. Okay, this is the setup here. If we take 11C5 and put that into our calculator, we're going to get 462. 2 to the 6th power is going to give us this 64 that's right here. And negative 5 to the 5th power is going to give us negative 3,125. And we're going to have to the a to the 6th and b to the 5th. So if we put all this together here, we're going to have negative 92,400,000, a to the 6th, b to the 5th. And so the coefficient for this is going to be negative 92,400,000. Okay. Let's do one more. I just feel like doing one more. Just want to make sure that we were clear on this. So let's say we have like 3x minus 5. No, it's not minus 5y. That's redundant there. Let's go minus 2y. And let's just say to the, 9th power. Okay. And out of just randomness here, let's go ahead and say, let's find the coefficient. The coefficient, doing the same process there, of x to the 5th, y to the 4th. Okay, so we're going x to the 5th, y to the 4th. Again, I'm setting this up so that the 5 and the 4 add up to 9. And we're asking what's the value that's going to be at the front of this. Okay, so let's set this up. A couple of easy parts here. We know that this 3x and this 2y are going to have to be 3x, and that's going to be raised to the 5th. And we have 2y, and that's going to be raised to the 4th. And it's a negative 2y, sorry, because of the negative that's there. So that's the easy part. We're going to have that 3x to the 5th, and we're going to have that negative 2y to the 4th. And we're just using the 5 and the 4 that are there. Okay. For the coefficient here, remember that this portion right here is going to be n minus r, and this is my r right here, right? So that means that when we're looking at this, it's going to be that there's 9 total terms, c, and remember the r is 4. That's it. So if we go ahead and put this in 9c4, let's put this in here, 9, whoops, function, go to the bottom, and we're going 9, comma, 4. That's 126. So this is going to be 126. We have 3 to the 5th power, which is 243, x to the 5th. We're going to have negative 2 to the 4th power, which is 16y to the 4th. And now we have to take 126, 243, and 16 and multiply those together. 126 times 243 times 16, and we have 489,888. 489,888, x to the 5th, y to the 4th. That's it. Okay. That's it. So just follow the formulas. They're really not too challenging. I'm confident you guys can handle this. It's a pretty easy section. It's just that you have to pay attention to all the little details as you're doing this, okay? Take care. I believe in you guys. Don't forget to like and subscribe to my channel. Be safe, be respectful, be responsible. Have a wonderful day. You take care.